Chapter 2 Single Area OSPF v2 Configuration. There are 6 sessions in this chapter. 2.1, that's the OSPF Router ID. 2.2, point-to-point OSPF networks. 2.3, multi-access OSPF networks. 2.4, modify single area OSPF v2. 2.5, default route propagation. 2.6, verify single area OSPF v2. Let's begin with 2.1, the OSPF Router ID. Before we begin configuring OSPF, let's first examine the network topology that we will use throughout this module. As shown in the figure, the network consists of 3 routers, R1, R2, and R3. Each router has already been assigned IP addresses on its interfaces, with no routing has been configured yet. This means there are no static routes and no dynamic routing protocols running on any of the routers. At this point, each router only knows about its directly connected networks. All router interfaces, except loopback 1 on R2, belong to the OSPF backbone area, area 0. This backbone area is the core of every OSPF network, and all other OSPF areas must connect to it. Let's take a closer look at each router. R1 has a loopback interface 10.10.1.0/24, which represents a local LAN. It is connected to R2 using the 10.1.1.4 with a subnet mask 30 network, and to R3 using the 10.1.1.12/30 network. R2 is the center router. In the topology, it has loopback 0, the 10, 100, 2.0/24, which simulates another LAN. It also has loopback 1, 64, 100.0.0/30, which represent a connection to an Internet Service Provider, or ISP. Notice that the loopback 1 is not part of the OSPF routing domain because it represents the external Internet. R3 has loopback 0, 10.10.3.0/24, to simulate its local LAN. It connects to R1 over the 10.1.1.12/30 network, and to R2 over the 10.1.1.8/30 network. Notice that the 3 routers from the triangular topology, this provides multiple paths between routers. For example, R1 can reach R3 directly or indirectly through R2. One of OSPF's key advantages is that it automatically calculates the best path based on interface cost and can quickly adapt if a link fails. You may also notice that loopback interfaces are used instead of actual LANs and WAN connections. This is a common practice in networking lab because many training routers only have 2 physical gigabits Ethernet interface. By using loopback interfaces, we can simulate additional network without requiring extra hardware. Throughout this module, we will configure OSPF so that all routers can learn about each other's LAN automatically. Once OSPF is running, each router will build a complete view of the network, calculate the shortest path using the shortest path first, SPF algorithm, and install the best routes into the routing table. By the end of this lesson, the routers will be able to communicate with every internal network in the OSPF routing domain. While traffic destined for the Internet will be forwarded toward the ISP through R2. We'll use the router OSPF followed by the process ID command to enable OSPF version 2. And after entering the router OSPF process ID command, the router enters router configuration mode, as indicated by the R1 parenthesis config hyphen and router with a pound sign. Like most other Cisco commands, if you put a question mark, you can see the available options, attributes for the command. 2.1.3 Router IDs. Before an OSPF router can exchange routing information, it must have router ID, often abbreviated as RID. The router ID is a 32-bit value that is written in the same format as the IPv4 address. For example, a router ID might be 1.1.1.1 or 10.10.10.10. However, it is important to understand that the router ID is simply an identifier. It does not have to belong to any actual network or interface on the router. Think of a router ID as a router's name or fingerprint within the OSPF network. Just as every student in the classroom has a unique student ID, every OSPF router must have a unique router ID so other routers can identify it correctly. Every OSPF packet that a router sends includes its router ID. This allows neighboring routers to know exactly where the information originated. A router cannot participate in any OSPF domain without a router ID. Before OSPF can form neighbor relationships or exchange routes, the router must first determine its router ID. The router ID can be assigned in two ways: manually, by the network admin using the router ID command. This is recommended method because it gives predictable and consistent results. And another way is, of course, automatically, where the router selects a router ID based on its configured interfaces if one is not manually specified. 2.1.4 Router ID Order and Procedure. So how does OSPF determine the router ID? Cisco routers derive the router ID based on one of the three criteria in the following preferential order. 1. The router ID is explicitly configured using the OSPF router ID, the RID router configuration mode command. The RID value is any 32-bit value expressed as an IPv4 address. This is the recommended method to assign a router ID. Second, if the router ID is not explicitly configured, the router chooses the highest IPv4 address of any of the configured loopback interfaces. This is the next best alternative to assigning a router ID. 3. If no loopback interfaces are configured, then the router chooses the highest active IPv4 address of any of its physical interfaces. This is the least recommended method because it makes it more difficult for administrators to distinguish between specific routers. And now we have three flowcharts to describe this procedure. The most preferred way is here. You can think of a router ID selection as a simple decision tree. The first one is a router ID manually configured? If it's yes, we use it. If it's no, continue. And then the next question is, are there any loopback interfaces? If yes, use the highest loopback IP address. Otherwise, continue. Use the highest active physical interface IP address. The router always stops as soon as it finds the first valid option. 2.1.5 Configure a loopback interface as the router ID. Now let's apply the router ID selection rules to our reference topology. Let's begin with router R1. R1 has two active physical interfaces, the Gigabit Ethernet 000 with 10.1.1.5 and the Gigabit Ethernet 001 with 10.1.1.14. For router R2, it also has two active physical interfaces, the Gigabit Ethernet 000 with IP 10.1.1.6 and the Gigabit Ethernet 001 with 10.1.1.9. Between these two addresses, 10.1.1.9 is higher. Therefore, R2's router ID becomes 10.1.1.9. Finally, let's look at R3. Its active interfaces are Gigabit Ethernet 000 with IP 10.1.1.13 and the Gigabit Ethernet 001 with its IP 10.1.1.10. The higher address is 10.1.1.13, so OSPF selects the 10.1.1.13 as the R3's router ID. Now let's learn how to configure a loopback interface on R1. First, we need to go to the interface configure mode for R1. So use the interface and then followed by the interface ID or name. And then in the interface configure mode, we enter interface loopback 1. After that, enter the address with the subnet mask. So the command is IP address 1.1.1.1 and 255.255.255.255. So R1 will use IP v4 address 1.1.1.1 as the router ID. Next, we use the end command to exit this configuration mode. You can verify the configuration using our popular show command. So this time we use show IP protocols and then use an option, but add a pipeline first. The option is include router ID. Now we can see that this router ID is 1.1.1.1 as expected. (2.1.6) Explicitly configure a router ID. Now let's look at the update topology. Unlike the previous example, these routers are not using automatically selected router IDs. Instead, each router has been assigned a manually configured router ID, which is the recommended practice. As shown in the figure, R1 used the router ID 1.1.1.1, R2 used the router ID 2.2.2.2, R3 used the router ID 3.3.3.3. Notice that these router IDs are easy to recognize and remember. They are also independent of the router's interface IP addresses. For example, R1's router ID is 1.1.1, even though none of its interfaces use that IP address. This demonstrates an important concept. A router ID does not have to match any interface address. It simply needs to be unique with the OSPF routing domain. This approach offers several advantages. First, the router ID remains consistent even if the interface IP addresses are changed. Second, it makes network documentation and the troubleshooting much easier. When you see router ID 2.2.2.2 in an OSPF neighbor table or debug output, you immediately know the information comes from R2. Finally, manually assigning router IDs prevents unexpected change that could occur if the router was selecting its router ID automatically from the interface addresses. Use the router ID followed by the RID router configuration mode command. We can manually assign a router's ID. For example, as shown here, in the global configuration mode for R1, you enter router space OSPF space and 10. Now we enter into the router configuration mode. Over here, we give the RID. So use the command router-ID and then put a space followed by the ID name. That is 1.1.1.1 and then end this configuration mode. Use the show IP protocols with the attribute include router ID. You can verify this configuration. 2.1.7 Modify a router ID. After a router selects the router ID, an active OSPF router does not allow the router ID to be changed until the router is reloaded or the OSPF process is reset. In this example for R1, the configured router ID has been removed and the router reloaded. Notice that the current router ID is 10.10.1.1, which is the loopback 0 IPv4 address. The router ID should be 1.1.1.1. Therefore, R1 is configured with the command router-ID 1.1.1.1. Notice how an information message appeared starting the OSPF process must be cleared or that the router must be reset. So in this command box, under R1, you enter show IP protocols, and then followed by a pipe, include router ID, and you confirm that the router ID is 10.10.1.1. And then you use the config T to enter into the global configuration mode for R1. Use the router OSPF 10 command and then to enter into the router config mode. Use the router-ID 1.1.1.1 to apply the change. After that, use the end command to exit router config mode. Make sure to use the clear IP OSPF process to reset this. And now you use the show IP protocol pipe include router ID, and you confirm that the new router ID becomes 1.1.1.1.